introduce today's speaker, Professor Jonathon Bray from the University of California at Berkeley. He has bachelor's degree from West Point and a master's degree in structural engineering from Stanford and PhD in geotechnical engineering from Berkeley. And he has been working in the field of earthquake geotechnical engineering for nearly 30 years, I guess, and has made really significant contribution. He has received several prestigious awards, like the Prakash Award, which is probably one of the most prominent in geotechnical earthquake engineering. And he has delivered Joiner Lecture, which is the upfront lecture in seismological science and engineering in the US. And he is really internationally recognized for his work. One really prominent feature is that he covers a wide areas in earthquake engineering, starting from source mechanism, ground motion, slope stability problems, and liquefaction. We are fortunate to have him here as an Erskine Fellow. So he's staying with us for a couple of months. And in addition to that, he has made a really fantastic contribution in the investigations and research work around Canterbury earthquakes. He has visited for several times, and I'm especially grateful for his effort in that regard and his support. He is coming back again next year for 3 months on his Fulbright Fellowship. And as I mentioned, since he is covering several very important topics, he will be delivering 3 lectures during this stay. The first one is today, and it is on seismic slope stability issues. Jonathan?
Thank you. Well, thank you for coming, and really it's been an honor. I mean, they really do it well here at the University of Canterbury. They bring you in, and I think I arrived about 9 o'clock on the flight in the morning. Mishko picked me up, and I was working in the office that afternoon. So that's really, somehow I got this idea there's a lot of work to do around here. And unfortunately, when I visit people, it's typically not a good thing because I chase earthquakes. But you know, one of our little taglines is turning disaster into knowledge. The Geotechnical Extreme Events Reconnaissance Unit, which we worked with the University of Canterbury and others in terms of doing the reconnaissance, it's critical to learn from these things and move on. And so I'll be talking about liquefaction in a couple of weeks, but you know, seismic slope stability is a very important area as well. And this work is work that I started at Purdue as an assistant professor back in 1990 and started looking at solid waste landfills and dams and now levees and such. And I've worked with a number of very talented PhD students. 2 of them, Dr. Travasarou works for Frugo in the Bay Area, and then Professor Rathje is a professor that is at University of Texas at Austin. The outline for the talk I'm going to give today is a brief introduction. You wouldn't be here unless you thought that seismic slope stability was important or were forced to be here because you were a student in my class. So then we'll get right into talking about, with the aim of looking at simplified methods, let's look at the components of a seismic slope stability analysis. And in fact, I want to go through these components because I think you should judge my method and other methods in this area by how well they capture the earthquake ground motion. How well do they capture the dynamic resistance of the system? How well do they capture the dynamic response of the system? And then do they do the calculations correctly and provide good insight? And then I'll talk about sort of the 2 bookmarks in terms of simplified methods. Really the landmark work is MCDC and C. Most senior engineers have performed MCDC 1978 type of analysis countless times, and they feel comfortable with it. And so now this new guy is coming along and going to propose that you should be now using the Bray and Travasarou 2007 method, and we'll see how that goes. Seismic slope stability is obviously very important. If you go to the 1964 Alaskan earthquake and you look at the 4th Avenue slide and what it did to the infrastructure of the city of Anchorage, it's obvious that, you know, a clay slope or a bootlegger cove clay, a sensitive clay, can undergo deformations, and that can lead to disastrous impacts in terms of the superstructure. We have countless earthquakes that show, in terms of landslides that are induced by earthquake shaking, and of course you had yours in the hills. in terms of projects, this is a landslide in Santa Barbara, Southern California, with Cotton Shires and Associates, where they had some static-induced landslides. And so obviously, in terms of fixing that, they have to also look at the seismic considerations. And then we have potential cases like this. This is actually a municipal solid waste landfill, a very nice way of saying we've got 60 meters of rubbish hanging over this very, very, very busy freeway. And if this is a slope of 1.3 horizontal to 1, if this fails and moves on top of this, that's not going to be a good situation. And so there's two critical design issues when we get into looking at seismic slope stability. I always want to step back. I'm known as the K guy, because we're going to see as we get in this lecture, we talk about seismic coefficient, and that's K, the seismic coefficient. People will call me up and say, give me a sense of what the seismic coefficient is for this project. And I'll always sit back and go, wait a minute, what's in the foundation of this thing you're talking about? What's the actual material comprised of, with the actual structure? Because nothing is more important in geotechnical earthquake engineering than the case where a material loses significant strength as a result of earthquake shaking. If you have liquefaction not only within the earth structure, but maybe in the foundation, that can lead to the dramatic flow slides that are disastrous. And so always step back and look at that problem first. The second most important issue is if you do not have materials that will lose significant strength, if you do not have a liquefaction problem below your structure or within your structure, then it's, will you get enough deformation that it might jeopardize performance? And so now we have to have some methodology for calculating seismic displacements, because that's going to be our measure of performance. Now, when I talk about this, I want to pull this in. This is a cutaway of a clay slope that was built in the laboratory on the shaking table at UC Berkeley. And we actually found that using spaghetti after dyeing it was excellent in clinometers, because they had about the same strength and resistance as this model clay. And so we could put this slope on the table, we could shake it, and then we could actually excavate back. We have a number of displacement gauges and accelerometers, but we can actually cut away and look at the displacement field. And one thing you see is that there actually is a failure plane that develops. You can see the offset in the spaghetti. And so there is a clean offset where one block is sliding over the other block, and that's partially contributing to the total horizontal displacement at the top of the slope. But very importantly, you also see distributed shear. So there's two components to when it comes to devatoric shear or distributed shear or shear-induced deformations. What I'm calling the Newmark type seismic displacement, it's the distributed shear within the sliding mass because it's not rigid. And of course, it's the actual sliding on the slide plane. Very importantly, I am taking volumetric out. There's obviously no volumetric settlement in a saturated clay with an undrained loading. But I think you should, at the minimum, even with a simplified method, you want to break the world into volumetric, how much shakedown do I get? And then you want to think about shear and devatoric displacement separately. Because, yes, those things that cause more devatoric of a slope will be tending to cause more volumetric. But for example, with a case with a saturated clay, that's not true. And so a lot of other methods mix these two, and I think that that's just fundamentally wrong. And so I'm going to say that my method is focusing on Newmark type displacements, which are focused on shear-induced deformations. If you have a system that's going to have volumetric shakedown, calculate that separately and then add that in to get the total displacement at the top of the slope. We can do this in a very elegant way with advanced numerical analysis with a fully nonlinear model. And so, for example, this is, before we cut it away, this is looking through the plexiglass. This is the original shape of the embankment. This is the post-deformation shape of the embankment. And you can see that it moved as a result of the earthquake shaking. We can calculate with Plaxis, for example, the deformation field, and then we can come up and get the fact that we have high shear strains here. And very importantly, we don't have failure develop along the entire failure plane at the same time. We tend to have failure develop at this location and then progress backwards. The black lines are what was actually recorded at 4 locations along this slope. The red lines are what we calculated with Plaxis. That's pretty good. So we can do really well analysis, but you know, let's be honest here in the sense that I can do well here because I have actually measured the base motion. It's great to do an experiment and know exactly what the motion was at the base. How many times do you have an accelerometer below your slope that has measured exactly the earthquake that you're going to feel that you have to design for? So recognize that these fancy analysis, the advanced analysis, are only as good as the input that goes into them. And there still is value to a simplified method to get you in the ballpark. And so let's talk about the simplified method, but first go through these components that I talked about. Number one is there is nothing more important than the ground shaking. We've had several studies on this from different fields, looking at bridges, looking at small buildings, looking at tall buildings, interstory drift, floor accelerations, liquefaction, pore pressure generation, seismic slope stability analysis. And when you do a full probabilistic analysis and you look at the uncertainty of all the things that lead to something like the uncertainty of the interstory drift, nothing is more important than the ground motion, the characteristics of the ground motion. And so if you're going to invest your effort, make sure you start off with a good characterization of the ground motion. The only thing that fully describes it is a time history, an acceleration, velocity, or displacement time history. But we often like these simplified parameters, such as peak ground acceleration. Now, obviously, we've known for some time that peak ground acceleration can't tell us everything that's important. It's amazing how many times we get into arguments and debates with regulators and reviewers about what the PGA should be, when in the end, it's not the most important thing. There's other important things like frequency content and duration. Duration is critically important to any kind of deformation-based analysis. The more significant cycles you have, the more cycles of slip you have. You know, the structural engineers got it right a long time ago when they basically came up with the concept of using an acceleration response spectrum at 5% damping because it captures the intensity and the frequency content of the ground motion. And again, in that study that we did for the Pacific Earthquake Engineering Research Center, where we all tried to find a better way of characterizing the ground motion, we all came back and said, I don't completely give up because this works a little bit better in this short period range, this works a little bit better in the intermediate period range, but for every problem we looked at across the entire period range, we could not find something better than the spectral acceleration at the degraded period of whatever was shaking, whether it was a building, a bridge, or a slope. And so why not use spectral acceleration at the period of the system, because that brings in the intensity and frequency content. And if someone is fighting you about PGA, you go, you know what? You can pick the PGA. You pick whatever PGA you want, I'll pick the spectra and the ground motion, and I'll get it to be what I want it to be in the period range of interest. That's what really matters. There's no regulators in this room, are there? Because I'm giving away one of my secrets. Okay, then we get into dynamic resistance, and I want to spend a lot of time on this. If it's going to be a simplified method, I've got to give you some simplified equations. And so these are in the handout, and they're in papers, so you can pull them up. One's an infinite slope analysis, and the other one's a deep sliding analysis. These are ones that you can actually hand calculate. So if you happen to be out in the middle of the field, you can do those hand calculations. It's not that difficult to have your iPad or your computer with you, and most of you have pretty easy slope stability analysis programs, so you can calculate the yield coefficient pretty easily. The yield coefficient, remember, is that seismic coefficient that you apply. Is a horizontal coefficient that you apply to the sliding mass, where when you apply that, the factor of safety drops down to 1.0. So you're doing a pseudostatic analysis, and you're finding what seismic coefficient produces a factor of safety of 1.00. As in typical geotechnical engineering, when it comes to static or seismic slope stability, it's the geotechnical properties, it's the engineering properties that really matter. And so, for example, let's talk about clays, factors that affect strength of clays. We know that we can spend a lot of time coming up with the static strength of a clay. In an undrained loading, we might do a total stress analysis of that in an earthquake and say, okay, what's the static strength? How do we modify that for dynamic considerations? We realize that clays are viscous, and so there's a rate effect. So that tends to be something in the range of 1.1 or 1.2 or 1.4. We know we get like about a 10% strength increase for a log cycle increase in strain rate. But then we also know from laboratory testing that as we work the clay and cycle it, we develop pore pressures, and we reduce the effective stress, and we soften it, and its strength after that tends to be lower. And so that's a factor that brings things down. Another thing is progressive failure. It goes in line with the entire failure plane is not mobilized at the same time, and I'll talk about that in the next slide. The important thing here is the static strength is where we spend most of our time discussing, investigating, and arguing. And then it's very important then to select something that will bump it up because of rate effects, something that will bring it down because of cyclic loading, something that will also bring it down because of the progressive nature of the failure if you have a strain softening material. And that's how we get the dynamic strength. Clay does not have a dynamic strength. It has a dynamic strength that's dependent on the earthquake shaking. So it's entirely consistent to use different strengths for the same clay depending on the ground motion. If I hit this slope with a near fault forward directivity ground motion that has one pulse but it's really intense, I actually probably could take full advantage of the rate effect, and I don't have to take the softening due to the number of cycles because it's really a monotonic loading. It's just coming at it really fast. And so for that case, I might use a dynamic strength that's 1.2 to 1.4 times the static strength. On the other hand, if I have a backwards directivity or I have the alpine fault break and I've got a low intensity ground motion with a lot of cycles, I'm not going to get as much of the rate effect. I am going to get a lot of degradation. Maybe that's a 20% drop or more depending on the soil. And so for that earthquake, when I run it through my slope, I would probably use a dynamic strength that's less than the static strength. And so it is inconsistent to use exactly the same shear strength for a clay for different ground motions. It is correct to use different strengths because strength's a function of the ground motion. Very importantly, we're talking about peak strength here. If you have a material that loses strength as a result of earthquake shaking or deformation, you have to make sure that if you calculate 2 meters of displacement, you're going to be using residual strengths with that because it's going to get down to residual. If you calculate only about 15 to 30 centimeters of displacement, then okay, you can use peak strengths. Always make sure that whatever you calculate as a displacement is compatible with the strength that you assumed. I want to talk about this progressive failure because that's something that hasn't been talked about as much. And the best way of looking at that is we took some model clay and we put a really small vein in it, 2.5 centimeters, a bigger vein, and then we actually put it in a box and kind of did a direct shear test. And this is the actual measured shear stress versus displacement of the small vein, the medium vein, and then the large test. If we think about the block moving, this clay right there actually immediately gets up to peak and it starts getting down to residual. This clay here might have just passed the peak strength because the deformation here, because this is compressible material, we're moving the slide versus that the bottom side, this might have gotten down to just past peak. This clay is just finding out that it's starting to get mobilized. And so when you smear those, you actually get this. We've actually done model testing where we use this at the element level and break this into a bunch of little elements and use properties that are dependent on the stress deformation behavior, and we can actually match this. The important thing here, it's a good and a bad. Good is it's more ductile. We're always worried about brittle failures. When you start smearing things, because you're not achieving failure along the failure plane all at the same time, it kind of smears things a bit, and it's a little bit more ductile than what a vein shear in the field would suggest. On the other hand, the strength, because you're not mobilizing the peak at every element level at the same time, is actually less. So it's typically a 0.9 factor. Now into the third component, the dynamic response of the sliding mass. I like to go back to this because Seed and Martin in 1966 wrote a classic paper. In fact, before you read any of my papers, you should read Seed and Martin 1966. And I love this too because they borrowed this idea of an equivalent acceleration from a brilliant structural engineer named Anil Chopra, who was a graduate student who was doing this thing looking at dams, and Neil Chopra's made tremendous contributions in looking at concrete dams, and he recognized that concrete wasn't rigid, and so he developed this idea of this equivalent acceleration concept. Seed and Martin were smart enough to borrow that idea and bring it into geotech, and that's the basis for the MCDC seed method, and you're going to see that that's also what we did later. But this is looking at a very, back then analysis was very costly, so this was a very simple equivalent linear analysis with assumed shear modulus and damping, 30 meters high, very triangular, and they just run the time history through, and they're kind of looking at what the acceleration profile right through the middle of the dam looks like at different times. Very important. I mean, early on, maybe things are coherent, and everything's shaking back and forth together. But for example, at 1.5 seconds into the strong shaking, the top is accelerating to the right, the bottom is accelerating to the left, and the middle is not going anywhere. And so I cannot use the acceleration at the base and apply that. I can only use an acceleration at the base if I believe what's above me is rigid. 100 feet of soil is not rigid, so I can't. I mean, look at this case where I have my maximum acceleration to the left. Look at the same way. To the left with your, at the crest is the maximum acceleration there, but the actual acceleration at the base is 0. So this is why they came up with this equivalent acceleration concept. The idea is you take a sliding mass and you realize that it's not a rigid block, it's deformable. And so we take each differential mass within the system and you take the acceleration acting at that level, you add all those up, you divide by the overall weight, in this case, if you want a dimensionless coefficient, to get this equivalent acceleration. Okay? That is the correct thing to use if you actually have a deformable body. Now, because force is equal to mass times acceleration, you can make this even simpler by saying this equivalent acceleration time history is just the shear stress, the horizontal shear stress acting on the failure plane, if I kind of have a 1D case, divided by the total vertical stress acting at that depth. So again, this is, you've been working a lot on liquefaction because you've had a number of earthquakes that reminded you how important liquefaction is. This is not dissimilar to R sub D, okay, with the whole idea that you take this incoherence in and you have a reduction factor because of that. I call this the equivalent acceleration, horizontal equivalent acceleration, to emphasize it's horizontal. The maximum value is the MHEA, and Kmax, which is the maximum seismic coefficient, the index of the maximum load, is this MHEA, which is in units of G, divided by G, so it's just this value without the G. So let's look at what affects Kmax. And the work done by Ellen Rathje and myself shows that Kmax, this dynamic loading for a range of ground motions, I think we used a suite of about 80 ground motions. We used different profiles of foundations, different soils on top in terms of the sliding mass, and we found that Kmax varied as a function of PGA of the rock, which makes sense. If you double the rock motion, you probably double the intensity. But soil response is nonlinear, and so that's why we have a nonlinear response factor in there. So it's not just strictly double the ground motion, double the seismic loading. But very importantly, it's a function of the period of the sliding mass and the period of the earthquake. As the system gets softer and softer and it walks away from where most of the energy is located, it's not shaken as hard. The seismic Kmax value is not as high as it is when you're basically near resonance. It also, this kind of result tells you that, near resonance, I can get really low responses and I can get really high relative responses. And so a simplified method and even a fancy, an advanced analysis is going to be a much more difficult thing to do when you're near resonance, because every little detail is going to matter. But the simplified method might work really well because there's a nice controlled systematic reduction as you're walking away from where the energy is located. This is kind of focused, or a resonance is at 0.5 instead of 1 because I'm using the initial period of the sliding mass. I'm not using the degraded period. And so Kmax, this maximum seismic coefficient, is a function of the stiffness and the geometry of the sliding mass. And so a good index of that is the fundamental period. And so if you actually have something that looks like this, you can just say, okay, 4H over VS. If it's something like this, you can say, okay, that looks a little bit like it's 1D. I'll come up with an approximate equivalent H, and I'll use that as my estimate for my dynamic period. And if you look at a 2D section, some nice work done by Ambrosius and Sharma show that that is 2.6 times the total height divided by Vs. And so estimating the shear wave velocity of the potential sliding mass material, its stiffness, and then having a sense of geometry is important because what shaking matters. Is it a very short structure or is it basically a longer structure? Then there's the actual calculation, and this is something actually, there was a lot of work done on this in the 60s and the 70s, but we've converged to a methodology that does this double integration very nicely. It's very important to remember that the initial Newmark analysis is a rigid block on top of a rigid plane shaking back and forth, and when you exceed the yield acceleration, you start to get slippage, and you keep on getting sliding until the velocities coincide. And so there's a number of very restrictive assumptions. Key parameters, the yield coefficient we've talked about, that's the maximum dynamic resistance. The seismic coefficient Kmax is the maximum seismic loading. Obviously that ratio is important, and so if it's greater than 1, we essentially have no displacement. If it's less than 1, we get displacement. Driving this point home, this is actually a large landfill, so relatively 45 meters high, relatively softer material, so it really shows the importance of incoherence. And I'm looking at rigid block assumption versus a deformable sliding block assumption. And I'm looking at sliding along the cover, which is just about a meter down, at mid-height, along its base, and just letting you know that I put the same rock motion in these columns that we're analyzing. What we see is for base sliding, the equivalent acceleration, because it takes in effect the incoherence of the motion, is significantly different in terms of its characteristic than the acceleration time history. If you calculate an acceleration time history at a point and you double integrate that with the Newmark method, you're assuming everything above is rigid, and that's not right. If you're down 45 meters into a waste fill, that's relatively soft. That assumption's not bad if you're only a meter into fairly stiff soil. So you can use the calculated acceleration time history directly to double integrate with the Newmark method to get the right answer if it actually is nearly rigid or incredibly stiff. That's really what Seed and Martin saw, and then that was incorporated in MCDC and Seed. And in fact, Bob Whitman, when he did a review of this, he kind of started calling it the decoupled approach. Because what you do is you say the system's not rigid. People who just use an acceleration time history are assuming it's completely rigid, and that's wrong. They improved it by saying, well, no, it's an actual system that has flexibility. It doesn't have a period of 0. It has a period of a half a second or 1 second or 0.3 seconds. It has some dynamic response. And so they use something like quad 4 or flush or shake or DMOD or Plaxis to calculate the dynamic response of the sliding mass. Then they use that equivalent acceleration time history, double integrate it with a Newmark analysis to calculate displacement. Now you can see the reason why it's called decoupled. It's obviously wrong. This method assumes continuity of displacement. There is no slip on the slip plane. And then I'm calculating a response and then calculating slip on the slip plane. So this is an improvement over the rigid block assumption, but it's not correct. And so actually Anil Chopra in 1991 realized that and came up with a fully coupled analysis for a concrete dam. And Ellen Rathje and I said, well, that's really nice. Let's take that and make it into a soil, use the right functions for that, and do the same fully coupled analysis. And so we developed a technique that does a fully coupled analysis. So the system is shaking back and forth, and when you exceed the acceleration at the base, and it can no longer sustain that, it starts to slide. And while it's sliding, it's still shaking back and forth, and you capture all of that at the same time. Now that we have this better way of doing things, this more correct method, it's been validated by some simple model tests where we shook not just a rigid block on a rigid plane, but we took soils of different stiffnesses. We find that the decoupled approximation, this is looking at the difference. And so when we're on the high side here, the decoupled method is conservative. The method that most people use, the decoupled approximation of MCDC, is typically conservative. It's not overly conservative until you get to really large displacements, but when you get to really large displacements, you probably know you already have a problem anyway. So in the range of engineering interest, it's not a bad method. There are some cases where it's unconservative, and those cases are forward directivity, near fault pulses. Now, some of this data is forward directivity, near fault pulses. So when you're close in to an earthquake and you get a pulse, if that pulse just happens to line up, you can have greater displacement with the fully coupled method, and sometimes you can get less displacement. We just don't really understand those trends as well. The most important thing to do is let's say you do a decoupled analysis, is to run scenarios and say, you know, I have two generalizations. I have generalization A, which I think is my best estimate of my soil properties, shear wave velocities and dynamic properties. But there's another realization B, which it could be shear wave velocities could be a little bit higher or a little bit lower and slightly different. Run those different scenarios for each ground motion. In this case, I'm just showing you 5 ground motions run for each of those 2 scenarios. You start to plot this up. Don't just calculate the displacement at the yield acceleration, but calculate it at lower yield accelerations and higher yield accelerations, so you get a sense of how sensitive are the results to minor variations in yield acceleration. Because we know as geotechnical engineers that we don't know the shear strength of clay to 2 significant digits, or definitely not 3. And we know that we have uncertainty in these kinds of things, so we want to use this as an index. In fact, I like to flip it around and look at it as a cliff. If I'm here, I could care less if it's scenario A or B. The ground motion doesn't matter as much. A lot of the things don't matter. I don't need to spend more of the client's money figuring out details, because with large uncertainty in KY, I get the same answer. Safe, low displacements. I don't care over here. Regardless of what's going on, I've got large displacements, and I don't need to invest the client's money to basically say I've got a problem. The simplified method, or these kind of decoupled analysis, when you get answers in here where I'm not sure if it's here or if it's there, and that's the make or break line, that's where investing in more advanced analysis, better site characterization will pay off. So, in fact, in reports, I always call it the calculated seismic displacement, to remind myself and the client that this is a calculated number. I don't actually believe that this slope's going to move 15 centimeters. It's going to move around 5 to 30 centimeters or so, something like that. And so it's an index of performance, but it's still very useful, because there's cases where it's small displacements, there's cases where there's large displacement, there's cases where there's moderate displacements. In fact, for many projects, and it depends on whatever the performance objectives are, you can have small displacements. In fact, you don't ever want to say 0, you want to say negligible, you want to say small, minor, you want to give some range, 0 to 15 centimeters or 0 to 5 centimeters is the calculated range. You might have cases where you have large displacements, and maybe for this system, more than 1 meter means that you have to remediate, you have to do ground modification, you got to do something special like that. And so it doesn't matter whether it's 2 meters or whether it's 4 meters, it's more than what's acceptable. And then moderate is somewhere in between. It's critical to evaluate what this means to the system. And I always like to step back and go, well, what are the consequences of failure? Is it a tailings dam that has a number of people living downstream of it? Or is it something that's 5 meters high and it's dry land on both sides of it? What kind of conservatism did I use in developing the seismic hazard? Did I use a 500-year return period, or did I use a 1,000-year return period? And then key thing is ductility. Are there ways for me to if I'm going to get a lot of sliding and I have a critical system that can't withstand that level of sliding, can I put a slip layer in a certain location that will let it slide there, as opposed to letting it slide wherever it wants to slide, which might be through my critical system. And so there's ways of engineering with that. With that background, I want to take 2 critical analyses, and I'm going to try to be objective, but obviously I can't be fully objective because one of them's by me, of 2 well-used simplified methods, okay? MCDC, 1978, Bray and Travasarou, 2007. So let's look at this great landmark paper. There's 4 or 5, 6 steps, and we'll go through them. Number one is they very carefully talk about strength. Even though they're coming up with a new method for doing seismic calculations of seismic displacements of slopes, they spend quite a bit of time talking about those things I talked briefly about, reduction in strength due to cyclic loading and things like that. And what they say, if it's significant strength loss, don't use the method. If it's slight, they say use a small reduction. And the reason why, limit equilibrium has a rigid, perfectly plastic. Real soil is nonlinear. So what they're realizing is if you cycle up to 90% of the peak strength over and over in time, you will accumulate distributed shear. They didn't call it distributed shear, but they're saying before you actually get localization and failure, you can accumulate deformations. And so that's why they're saying use a small strength reduction. You calculate your yield coefficient based on geometry and the strength. This is my biggest headache with their method. All you have to do is do what I have found in my experience to be the hardest thing in the world. Estimate the peak ground acceleration, including topographic and side effects, at the crest of a slope. That is one of the witchiest numbers in the world to estimate. It's all over the place. And here's an assumption. Here's an example. Here's some work done by Ellen Rathje and I, where given different rock motions of different intensities and different soil profiles, realizations, this is our estimate of the PGA, or the maximum horizontal acceleration, at the top. There's a bit of scatter there. And so there are 2 types of engineers in the world. There's top-down engineers and there's bottom-up engineers. I started off life as a geotech when I transferred over from structures looking at fault rupture and how a fault comes up below a dam and impacts that dam. So I became a bottom-up engineer, and I've continued with that. And so that's why my methods kind of focus on the rock motion, characterizing that, and then seeing how it responds to the soil. This is kind of a top-down approach where you're getting the crest motion and then you're using that to go down and figure out the loading. This is a really hard thing to do. If you have that, then this is a lot like R sub D, is as you go deeper and deeper, you get more incoherence, and so Kmax becomes a smaller percentage of the crest acceleration. But realize Kmax can't be more accurately estimated than the peak ground acceleration at the top. The reason why I got into this is my first consulting job, I got involved and I did a fancy 3D dynamic analysis of a dam, and then I checked myself with MCDC and SEED, and I got a value of Kmax over PGA out here. And so I knew I was wrong. And then I thought about it after checking it and realized they did one finite element analysis. Phase MCDC had cards back in those days, and he had to wait and pray that the computer would run those cards properly, and so he did one finite element analysis. You cannot get a PhD at University of Canterbury, UC Berkeley, anywhere running one finite element analysis anymore, okay? But back in the 70s, that was a big deal, and then he ran something called a shear slice method, a very approximate method, and he ran it for about 6 ground motions. Okay? And so a lot of people think of these as bounds. Never call these upper bounds and lower bounds. They are not. If you actually look at the range of possibilities, it goes all the way out to here to all the way out to there. Why does it vary in this way? It varies as a function of the period of the sliding mass. And when you look at the details of this uncertainty, there is some systematic variation within that chaos, and it's the period of the sliding mass. Then, given that Ky and Kmax ratio, you come in, the things that's missing is duration, so they use magnitude as a proxy for duration, and then you estimate displacement. This is on a log scale. One thing when I teach this in short courses in the US, I always get somebody running out the room. The famous MCDC paper, they never corrected it, has an error in it, and if you use the actual chart that's in the original paper, you'll only be off by a factor of 10. So read that paper, study that paper, but do not use the charts in that paper. Everyone knows that, right? Okay. The late Professor Harry Seed was my mentor, brilliant person, and I always listened to him. And he said, and I quote, "It must be noted that the design curves are derived from a limited number of cases." He did a great job back in the early 70s. Amazing how little data Harry Seed had to do such incredible fundamental work that got you maybe 60 to 80% toward the solution. He kind of knew what the answer was before you even did your Feynman analysis, and then you kind of proved what he already knew. He had this gift. But he ordered me. He said, "These curves, Professor Bray, should be updated and refined as analytical results for more embankments are obtained." For some reason, as great as this work is, it's kind of gotten entrenched as being correct. And it's almost wrong to challenge it. Nobody uses Seed and Idris 1971 liquefaction triggering curves. We've moved on to Youd et al., we've moved on to Idris and Boulanger, we've moved on to the Seed et al. Method. But for some reason, engineers have a hard time letting go with McDC and Seed, even though late Professor Harry Seed said, hey, if you get more data and you can do better, you should revisit this problem. Why? He used a very limited number of ground motions. He used the PGA at the crest, which has a lot of uncertainty. He used a very simple method, shear slice method, decoupled analysis. The upper and lower bounds are not there, and we're trying to get more into performance-based engineering. There's no estimate of uncertainty. So let's look at it another way. Let's look at the Bray and Travasarou method. Not smarter, not better, I just have more data. He or she with more data should win. So we're going to do a fully nonlinear, fully coupled, deformable stick slip analysis because we can with our computers. We're going to go ahead and say, oh, let's use 8 different TS values, 10 different KY values, so we have 80 of those cases. And this is the most important thing, the ground motion. So let's take all of the ground motions from the NGA database that was available for shallow crustal earthquakes, and let's use all the ones that are within 100 kilometers for 41 different earthquakes, run them through, and let's have Thayer run 55,000 analyses so you don't have to. First thing to do is, after you've done 55,000 analyses and you pat yourself on the back, you go, okay, what do we do with this? Okay, this is not data. These are analytical results, but we can start examining them like they were data and say, well, what's the most efficient ground motion parameter? For example, is it PGA? You take the PGA of each record and correlate displacement versus PGA. How about spectral acceleration at 1.5 TS? Or how about areas intensity? If the world was all stiff, weak slopes, it would be areas intensity. And it captures the intensity, frequency, content, duration. It's the one measure that's best if things are actually driven by acceleration. But we're going to look at ranges. And so this is actually KY of 0.1. This is KY of 0.2, both for a half a second sliding mass. This is same KY, but now we're going with a longer system, 1 second. So we're kind of looking at things that are weak and stiff, and then we're getting into things that are weaker and more flexible. In this direction, they're stronger and stiff, and then eventually we get to being stronger in a relative sense and also more flexible. We actually we looked at 32 parameters, and I even came up with ones called the Bray index, because this is my chance. Arias got famous, but I wanted the Bray method to work. I wanted the Bray parameter to work. It was a brilliant idea, but it didn't work. So you don't see the Bray one up here. But what you see is PGA. I actually picked it's always good to pick some that will not work, because it's always a good sanity check. It better not work. Duration by itself doesn't work. Peak ground displacement by itself doesn't work. Some of the most promising are spectral acceleration at the degraded period. That's why the 1.5 is there. This is the initial period, but with seismic shaking and induced strain, we actually get some deformation and we get some softening. So that's why the 1.5 factor is in there. The red box is Arias intensity, and the green box is the Hausner spectral intensity. And what you find is, for example, if I actually have a weaker stiff slope, Arias intensity works the best. These are the standard deviations, so the smaller the better. But, for example, it doesn't do as well for a flexible system, because in fact, Hausner's spectral intensity does better for a flexible system because it's out in the velocity range. The one parameter that works the best over the entire period range is spectral acceleration at 1.5 TS. So we're going to use that as our characteristic of the earthquake. Then, we did the regression. You always do these regressions at least 3 times. And the first time we did it, we were finding that data, whether it was 0.0001 millimeters or 0.00 millimeters or 0.1 millimeters, that's a big order of difference mathematically, and that was basically causing the form of our regression analysis. Then we got out of our mathematics room and we said, we're engineers. Those are all the same number to me. Those are 0. And so we said, we can't let that data cause our regression to go the wrong way. So we're going to basically say, anything that we calculate that's less than a centimeter, for all intents and purposes, is 0. And so we want to predict when we get less than a centimeter. And so this is the probability of, quote, getting 0 displacement, as in engineering 0 is less than a centimeter. And you can see that it makes sense. As the yield coefficient increases, you're more and more likely to get 0 displacement. As the ground motion intensity increases, you're much less likely to get 0 displacement. And there is an influence of the period of the sliding mass. It's kind of almost the inverse of a spectra. And so we say, okay, we'll have a function that's derived or regressed on the data, the calculated data, as a function of these important parameters. Then we'll take all the other data that's greater than 1 centimeter and we'll regress on that, and it'll essentially be based on the same things, but we'll have to add in duration, and a proxy for duration is magnitude. This is a hard problem to do, so we're going to have high residuals. We're going to have high errors, okay? But that's what it is. It's a calculation of a seismic displacement. So this looks complicated, but once it's in a spreadsheet, and I made a spreadsheet available, so you don't even have to even look at these equations again. All you have to do as an engineer now is focus on what you're best at, and that is not interpreting 55,000 analyses. It's saying, okay, this is like a screening analysis. What's my chance of getting negligible displacement? I won't call it 0, I'll call it negligible displacement. Well, all I need to know is I need to know KY. That's where I should spend my time as an engineer. What is the actual yield coefficient? What are the strength of the materials? How do they change with different earthquakes? I need to be able to estimate the period of the sliding mass, because that matters. And then very importantly, I need to be able to estimate the spectral acceleration of the ground motion that's coming into my system. Then, if I get a case where the probability of zero displacement is low, so I'm going to get significant displacement, then I go into this regression analysis, and I use essentially the same parameters and add in magnitude and estimate that. So let's kind of look at the trends, what those results get you. I'm looking at a magnitude 7 strike slip fault at a distance of 10 kilometers at a soil site. So my system that's going to slide is on this deep soil site. This is what the response spectra looks like at 5% damping. If I put that into equation 1 and I plot the probability of 0 displacement going from 0 to 1 versus the period of the sliding mass versus different KY values, here's what I see. If I have a low KY, it doesn't matter whether it's 0.04 or 0.08, I am going to get a non-zero displacement. It's a weak system. For this strong motion, this close in, of course I'm going to get that. So I don't spend money on measuring shear wave velocity. I don't care what the shear wave velocity of the soil is. It doesn't matter. If I get into a case where I have a stronger system, then investing money into actually measuring, not just guessing or estimating, but actually measuring shear wave velocity might save your client a lot of money, because I get a low probability if I have this as my period, but if I'm over here, I actually get a high probability of a 0 displacement. And so this is a nice way of getting a sense of what's important. For the case where I calculate displacement for this ground motion at this site as a function of the period of the sliding mass versus the KY, again, you can see that for low KY values, the influence of TS is not that important. But for some KY values, that influence is really important, and so you should invest the money to measure the shear wave velocity. You can take those two things and integrate it together, and you can do a full probabilistic analysis where you say, the client feels, and I've discussed this with them, that 30 centimeters is acceptable level of displacement. So I want to know what's the probability, given these earthquake scenarios, that I'm going to get a displacement greater than 30 centimeters. And this is showing that as a function of TS and the yield acceleration. I will most likely get less than 30 centimeters if I have a high KY value, regardless of what the TS is. If I have a really weak slope, I'm going to get more than 30 centimeters. But if it's an intermediate slope, I need to figure out what the period of the sliding mass is to be able to figure that out. You probably want to know if it works, and the only true thing is to actually run it against case histories. We ran through 16 case histories. These are just some of them, and I'll go through them real quickly. First, I'm looking at a subset. These are landfills, solid waste landfills, that were shaken by the Loma Prieta earthquake in Northern California in '89. This is the documentation of how much displacement there was in reality. So this is the reality column. And this is what our method predicts for the probability of zero displacement. All of these cases, they shouldn't have much displacement. And if there is a displacement, it's low. So that's a consistent response. This is a good index of that performance. Now we look at a couple of dams that were shaken by that same earthquake. And you can see the actual observed displacements, 50 and 15 centimeters respectively for the Austrian and Lexington Dam. The method says you're going to get displacement. You're close to a big earthquake. And the level of displacement from the 16th percent exceedance to the 84th percentile exceedance captures the range pretty well. Let's go to landfills that were shaken by the Northridge earthquake. This is the observed movement. We're going to get displacement, and except for one case, which is the one that will never work out for any one of us, is this one we underestimated. But the rest of them, it's working pretty well. So I'm showing you that's actually our worst case right there. And then this is too good to be true. I mean, I couldn't believe this. In fact, I still wouldn't believe it if I was in the audience. This is a dam in Mexico that was shaken by a number of events. They had really good instrumentation on it, so they had very precise measurements. Professor Elgamal at University of California at San Diego wrote a very nice paper on this. And there was a centimeter, maybe a little bit more than a centimeter, 4 centimeters. I'm not as concerned about nailing the actual numbers. I think it's more important to get the trends right. And the trend is, as you go from S3 to S4 to S5, you get more displacement. Does the method have the same trends? Well, the probability of zero displacement goes down, and the amount of displacement goes up. And it's actually maybe part luck and part greatness that it actually is in the ballpark. Now, Harry's seed is never wrong, and I didn't think that Bray and Rathje were not too far off either. So I'm not saying that what everyone's been doing is wrong. All I'm saying is now we have a refined tool. Because when you look at this, these are pretty consistent. You know, low displacements, kind of intermediate or larger displacements, low displacements. They're consistent. It's just we're doing better now because I have 688 ground motions and they only had 6. And Bray and Rathje only had about 80. Plus, I think I've gotten a little bit smarter in 10 years. Real quick example, and again, all these slides are available to you. This is actually Austrian Dam, but you don't know that, and it's next to I put it next to the Hayward Fault. It's not actually there, just as an example. First, we look and say, okay, there's no liquefaction, there's no soils, even clayey soils that will not undergo significant strength loss. That's always the first check. We have some undrained strength properties based on some triaxial testing that were taken from this system. The KY was calculated with a slope stability program. Because this is more triangular, I'm using the 2.6 H over VS, where that's the H. So I estimate 0.33. I look at my earthquake. It's a 6.9 at 1.1 kilometers. And so I go ahead and I calculate with reasonable ground motion models at that time what the spectral acceleration at a half a second is, because that's 1.5 times 0.33, which is the fundamental period of the sliding mass. I get about 1 g. I put that information into this equation. I calculate 0. You're going to get displacement. You probably didn't need to listen to my lecture to know that if you're 1.1 kilometer away from a 6.9, you're going to get displacement. But then how much displacement? It estimates a median estimate of 40 centimeters, and the standard error term is 0.66. What that means to you as a practicing engineer is whatever you think is your best number, double it, half it, and that's your range. And so the 16th percent to 84th percentile is about 20 to 80 centimeters. I'm not going to be able to even tell you that I can do better than that. Okay, that's the range. That's enough where if that range is too much, you have to do something. Most dams can handle this range of deformation and not have issues. But after presenting this, I found that there were a number of people who said, well, this is getting too complicated. Can we kind of make it a simpler thing? So I said, let's go back to the pseudostatic analysis. Pseudostatic analysis meets the criteria of being simple. It's a slope stability analysis that we're used to. All that we've added is a seismic coefficient to represent this incredibly complex level of shaking. So the only way this could work is if I calibrate my seismic coefficient, dynamic strengths, and factors of safety against either case histories, that would be the best thing, or through more advanced analysis. If I can train my simplified pseudostatic analysis so that it gets the right answer, or I'd say the answer that's consistent with what I would have gotten if I had done a more complex analysis, it might be a useful screening tool. One of the methods that's very famous, the Rankine lecture by the late Professor Harry Seed is in 1979. He said use appropriate dynamic strengths, use a K of 0.15. If your factor of safety is greater than 1.15, with a few caveats, life's good. Very importantly, this method is based on a meter of movement being acceptable. What happens if you have a system like a warehouse or a building or a house with lawyers in it where they think 1 meter of offset's too much? And then when I sit back and look at this, clearly a K of 0.15 for the entire country of New Zealand, the entire country of the United States, the entire world doesn't make sense. I mean, there's obviously, if you're right next to the Alpine Fault, that's different than being 100 kilometers away and maybe having some smaller faults close by. Also, the other thing is this factor of safety gives people this feeling of security. But realize when you calculate a factor of safety greater than 1.15, that's not necessarily safe because that's calibrated to a dam moving a meter, and that might not be acceptable. So don't be seduced into the safety of a factor of safety. Seismic coefficient. This seismic coefficient, this K, should depend on the level of shaking. We know that from looking at case histories and analysis. Things like distance to the fault, the earthquake magnitude, the dynamic response of the earth structure. It should depend on the criticality of the structure. It should depend on what is the acceptable level of displacement. So how do we choose this K? Well, we came up with this relationship. Why don't we calculate the K as a function of everything else? Instead of calculating the displacement as a function of a bunch of things including K, let's calculate the K as a function of the displacement and the seismic loading and everything else. And so we just do a little bit of mathematics and we turn things around, and so you say, okay, pick your displacement, characterize your seismic loading, your dynamic period of the sliding mass, your magnitude, put it in here and calculate the K that's compatible with this. This is exactly what Bob Whitman did for retaining walls in training his system. He basically came up with a method for estimating displacement given a bunch of things, and then he realized retaining walls are pretty simple structures. Why don't I turn it around and figure out the seismic coefficient that's consistent with that level of displacement and that level of shaking. This is insightful looking at the seismic coefficient. We know it's a function of obviously the level of displacement, the earthquake, which is its intensity, frequency content, and duration, and the period of the sliding mass. And so I'm going to keep the period of the sliding mass the same, 0.2 seconds, so it's a relatively stiffer slope. But I'm going to look at the seismic coefficient as a function of the intensity of the ground motion. Well, clearly, as the motion gets more intense, the seismic coefficient should increase. But notice the seismic coefficient also increases as you go to a more stringent level of displacement. If you say, I can let the thing move 30 centimeters, you can maybe use something 0.18. But if you say, no, 5 centimeters is the acceptable level of displacement, then you have to go with a much higher seismic coefficient. Okay? So you pick your seismic coefficient not just as a function of the earthquake ground motion, but also what you judge to be acceptable level of displacements. So this is the method, is obviously always check to see whether you have strength loss, use strain compatible dynamic strengths, select what you say is your acceptable level of displacement given the system and the uncertainty that you want associated with that, or the confidence interval that you want to have, estimate your period of your sliding mass, characterize your seismic demand. If you use a K that's calculated with that equation on a pseudostatic analysis, and you calculate a factor of safety greater than 1.0, then you are confident at the chosen level that you're not going to get more displacement than dA. So you can choose the acceptable level of displacement, characterize the earthquake, and then figure out the K that when you put it in a pseudostatic analysis, if you calculate a factor of safety greater than 1.0, you're fine. And everyone knows that factor of safety is actually not a really good parameter for static analysis, for dynamic analysis. You'd like, if something has a factor of safety of 2, you'd like it to be a certain same percentage safer than a factor of safety of 1.5 as 1.5 is to 1. It's highly nonlinear. So that's another reason why I don't like to use a factor of safety of 1.15 as my dividing line. Let's use 1.0, but train that to the acceptable level of displacement. Liam Finn liked this, and so he was part of a group that I went to Canada a few times, and they said, you know, we need to use this in a code. So let's even simplify the simplified method. Let's take a simple stiff slope and a simple intermediate slope. Let's assume that for most systems that we're designing these things for, they can accept 15 centimeters of displacement. And so that thing actually boils down into something that's actually now used in Canada for a screening analysis, is they pick a seismic coefficient that's tied to 15 centimeters of displacement. It's just a function of the intensity of the ground motion, which you can get from the ground motion maps, and magnitude, which is typically around 7.5, maybe sometimes 9, sometimes 7. I know this is right because for the typical case, 7.5, if you take 0.25 times SA, that's what comes out of this. We know that SA is about 2.5 times the PGA for most spectra. 2.5 times 0.25 is 0.65. Anyone who's worked in earthquake engineering knows that whenever you present something with 0.65 in front of it, it has to be right, right? So here it is, seismic coefficient. In fact, it's funny how we go around the world. The old timers in the 60s and 70s often said, you know what, if I pick a seismic coefficient that's about 60 to 70% of the PGA, won't I get something that's about right? Yeah, about. So, in concluding, first question is always, do you have materials that will lose strength? If not, then you look at the seismic displacement analysis. I propose to you that the Bray and Travasarou method is superior because it captures the deformable sliding mass. It has, I think, a nice way of capturing earthquake shaking, the spectral acceleration at the degraded period of the sliding mass and magnitude for duration. It uses what everyone uses for KY. It brings in the deformable nature of the sliding mass. It does coupled seismic displacement as opposed to decoupled seismic displacement. And in the end, this simplified method is useful because it focuses your attention on what really matters, and that is the earthquake characterization and the soil characterization. That's where you focus your attention, and then let this calculation get you in the ballpark. Thank you.